In problem number 1, they are asking us for the force between
the two spheres. So we have our data that it's charge that it's 3 microcoulombs, and the distance that it's 0.1 meters. So we substitute with the formula of force, we substitute our values, and then we have our result. In problem number 2, they are asking us for how many electrons does one charge, how many electrons does each charge has, and how many electrons will be removed from one another. First of all, we have our data that it's the mass, the distance, the force, and the charge of the electron. Then we're going to clear out with the formula of force our charge, and then we substitute our values, and then we have this result. Then we're going to divide the charge that we got over the charge of the electron in order to know how many electrons will be removed from one charge to another. Then in order to know how many electrons does each sphere have, we're gonna divide the mass of the copper over the molar mass times the Avogadro number times the atomic number, and this will give us how many electrons does each sphere has. In problem number 3, they are asking us for the electric field. So we have our data that it's 4 microcoulomb, that is the charge, and the force minus 8 times 10 to the minus 4. And we're going to use the formula of electric field, that it's force over the test charge. And we substitute our values, and we have this result. In problem number 4, they are asking us the time that the electron stop, and also the electric field and its direction. First of all, we have our data that it's velocity, distance, and the first step we're going to do is to take the acceleration with the formula of final velocity, the one that doesn't have time. Then we're going to substitute our values, the final velocity that is 3.75 times 10 to the 6th, to the square, the initial velocity, which is 0 because it starts at rest, the acceleration we don't change it because we don't have it, then the final position and the initial position. Then we clear out for the acceleration, and we got this result, and it's in negative because we are decreasing the acceleration. Then we're gonna substitute, we're gonna clear out for the time with the formula of velocity equals the initial velocity plus the acceleration times the time. And we clear out for the time, and we substitute our values, and we're gonna have this time. Then, and this is the time when the electrons stop. Then for the electric field, we're gonna use this formula, and we're gonna substitute our values. First of all, we need to know the force, and we're gonna use the mass times acceleration. We know the acceleration, and the mass is the mass of the electron. We substitute our values, and we have this result that is 2.28 times 10 to the minus 16 newtons. Then we substitute our values of the electric field, and because the force is negative, we're gonna divide it, and we have an electric field that is positive, and it will go outwards. In problem number 5, they are asking us to demonstrate that a charge outside corresponds to this formula. And we have this in a solid sphere. I draw this in order to understand that when we have a sphere, the charge is distributed in all the sphere. And when the distance, it would be from the center. We're gonna need to elevate the distance. When we have a charge in a sphere, the charge is distributed uniformly in in the solid sphere, and the electric field will be outwards because the distance will be elevated to the square. In problem number 6, they are asking us how many electrons, excess electrons, would be added to a plastic sphere with this electric field. And also they are asking us the electric field with this charge at 10 centimeters of distance. First of all, we need to clear out for the charge using the formula of the electric field. We clear out for Q, and we have our charge. Then, in order to know the electrons, we're going to divide the charge that we take out over the charge of the electron, and will give us this result. And for the electric field at 10 centimeters, we first part the centimeters to meters, and we substitute our values, and we will have this result. In problem number 7, they are asking us the work. So first of all, we have our data, that is the electric field, the charge, and the distance. And we're going to use the work formula, that is test charge times the electric field times the distance A minus the distance B. We substitute our values, and we have this result. In problem number 8, they are asking us for the electric potential of one charge, and with other charge they are asking us the electric potential energy. First of all, we have our data, that is distance, charge 1 and the charge 2. For the electric potential, we're going to use the formula of voltage equals to the constants times the charge over the radius, over the distance, and we're going to substitute our values with the charge number 1, that is 8 microcoulomb, and we have this result. And for the second charge, we're going to use the electric potential energy formula, that is the constants times the test charge times the charge over the distance. And we're going to substitute our values, and we have this result. In your sheet, you're going to see time -7, but it's -6.